Hello, everyone. So our project is titled as NYC Housing Price Prediction. So as we all know that the housing market of New York City has been in ups and downs in the last several decades due to the economic cycles. So for house investors and buyers to make purchasing decisions wisely, it might be useful to see what the driving characteristics of an expensive house are. So in this project, our group aims to predict the price of the house listings in New York City using selected features of the close by neighborhoods. We will perform regression analysis and optimize our chosen model to the best accuracy with feature selection, mall tuning, and other techniques. Meanwhile, the resulting model will create potential benefits in multiple areas beyond basic price protection, such as providing data, proven insights, enhancing a balanced leverage between the buyers and sellers, and also understanding the housing market in general. So coming to our methodology, it's basically that we collect the data set, then we do the data pre-processing, such as cleaning and stuff, and then we do the data visualization and apply the models. So regarding the data set, it has been collected from the NYC Department of Finance, which contains information about the sales of properties in New York City for the years 2020 and 21. It contains about 167720 property sales information pieces. And there are 21 features in total. And in this project, we will not study the effect of time on sale price. After the entire data cleaning process, the clean data contains 167783 rows and 19 columns. Our target variable is the sale price. So we have performed data visualization where we have discussed the best possible use cases and correlation among the data, and we have used libraries like Matplotlib and Seaborn. Coming to my teammates, they're now going to explain the implementation of various models.
We tried to implement different models. We experimented using different regression models. So for the performance metrics, we are using three measures. So they are R squared mean and also MSE and RMSE. So basically, R squared mean is the accuracy of the model. So it represents the proportion of dependent variable variance, which is described by the independent variable, and it is a statistical measure. So coming to the models, we started with a linear regression model. So it basically works by fitting the straight line to the data. And here we are getting a accuracy score of 48%. Then we move on to the lasso regression, which uses a shrinkage, which is basically a central tendency like mean to predict the data. So here we see a decrease in the accuracy score, getting 29% here. And then we implemented the ridge regression. It uses an estimator called ridge estimator, which basically helps us to predict the data using multicollinearity. So we are seeing an increase here in the accuracy by 48. So and finally, we have used in the linear regression model, we have used ElasticNet, which basically gives out a quite unexpected value, that is 29%. It uses both the lasso and ridge output variables. So rest will be explained by my teammate Vanita.
Yeah, thank you. Then now we tried implementing decision tree regression. It basically builds models in the form of a tree. It works by splitting data into smaller subsets in the tree, and as a result, we get a tree with the decision nodes and leaf nodes. And a root node is at the beginning of the tree, which corresponds to the best predictor. So this is a residual plot we got for the decision tree. Here you can see the accuracy score is about 31%. So we tried implementing a K-NN regression. K-NN regression is basically a non-parametric method. And by averaging the same observations in the same neighborhood, it approximates the relation between independent variables and continuous outcomes, meaning it tries to predict the value of output variables by using local average. So for that, we should set the size of the neighborhood, or by cross-validation also, we can find the size which minimizes the mean square error. So see, this is a residual plot for K-NN, and here the accuracy is about 51%, which is improved version from the previous model. And then we tried implementing light GBM regression, which is basically a fast and high performance gradient boosting framework based on decision tree algorithms. And it is used for ranking, classification, and many other machine learning tasks also. And this is the residual plot we got for the light GBM. And the accuracy we achieved here is about 62%. And then for random forest, we also tried implementing the random forest regression, which is a supervised learning algorithm. and it uses an ensemble learning method for regression, meaning it combines the predictions from multiple machine learning algorithms to make more accurate prediction than a single model. And it performs great on many problems like nonlinear relationships, etc. So this is a residual plot we got for the random forest, and the mean square is, and the accuracy we observed here is about 62%, which is obviously, it got increased from the previous model. Now my teammate Priyanka.
Okay. So we also implemented boosting algorithms in our project. Boosting is an ensemble technique in which the weak learners are trained, and in order to build a strong learner, basically it will select a random sample of data and train the model on it. And the previous and the next model will learn from the errors done by the previous model. This way we will get a stronger model. So we have implemented 3 models of boosting. First is CatBoost, second AdaBoost, and third is XGBoost. CatBoost uses decision trees as their learning parameters, and we achieved R2 score of 35%. And then we gradually improved it using AdaBoost, and we got 63% accuracy. And for the XGBoost is also a boosting algorithm, but it has a penalty term which helps to reduce overfitting on the data set. And the best accuracy is achieved on the XGBoost, which is 65%. Yeah. And the conclusion part will be explained by Anchal.
Okay, so in conclusion, we observed that basically XGBoost outperforms all the models with the highest R-squared score. One of the challenges that we faced during this project was the data collection and the lack of extensive and appropriate data. Hence, if allowed more time and appropriate data, we may incorporate the effect of COVID-19 on our housing prices after 2020 as well. Regarding the future scope of this project, it can be extended to multiple states, and this could be further developed to API for implementation of the price estimation of real estate properties. So that's about it. We did find that all our models accurately predicted the housing price. Thank you.
Thank you.